A 0.5 gram oil drop has a negative charge of minus 16 microcoulombs. And here's the mass. And it remains stationary, it's not moving, between two charged parallel plates 25 centimeters apart. Draw a free body diagram, show all the forces on the drop. Draw the electric field lines between the plates. Find the magnitude of the electric field required to keep the drop stationary. And what is the voltage difference between the plates? The mass of the drop decreases with time due to evaporation. Describe what will happen to the oil drop. Well, as always, start with the gravitational force here. mg is trying to pull the drop down. So for it to remain stationary, you need an electric force in the up direction, and since it's stationary, the acceleration is 0. Draw the electric field lines between the plates. The charge is negative. Okay, so if I need a force in the upward direction, the electric field points in the opposite direction to the electric force. So the electric field is pointing down. Find the magnitude of the electric field required between the plates to keep the drop stationary. Well, we start with Newton's second law, as always, right? Sum of the forces is ma. Electric force in the up direction, even though the field's going down, this is a negative charge, so the force is in the up direction. We've got the gravitational force, and we've got ma. But ma is equal to 0 because it's not moving. So the electric force is equal to mg. Well, F is equal to QE. Right? That's how we define the electric field by this expression. Electric field is force over charge. So I have QE is equal to mg. I'm solving for E. Divide both sides by Q. Now we just need to plug in our values to this equation. And the mass is 0.5 grams, but we need to be in kilograms. So you move the decimal over 3 places, and you get 0.0005 kilograms. Here's g, gravitational acceleration, and divided by the charge. It's microcoulombs, so it's going to be 10 to the minus 6. And here we go. Here's our electric field. And notice we're just looking for the magnitude here, right? It's 306 newtons per coulomb, and we know it's in a down direction. Why? We figured that out earlier in the problem. What is the voltage difference, or delta V, between the plates? One of my favorite equations. E equals delta V over D. And that only applies for a parallel plate configuration where D is going to be this distance. It's a distance between the plates. And it's my favorite because delta V equals Ed. And I know somebody named Ed. So delta V, here's our electric field, and we're just going for the magnitude here, times 0.25 meters, and we get a change, a delta in electric potential, or a delta voltage, or a voltage difference, a lot of different ways to say it, of 76.5 volts. Over time, the mass of the drop decreases due to evaporation. And this is why in the Millikan oil drop experiment, the first time people did it, they used water drops. But guess what? Water evaporates pretty quickly. So oil does not evaporate as quickly, but it will to some degree. So what will happen to the oil drop? We check out our free body diagram. If the mass of the drop decreases, the weight will also decrease. The charge is staying there pretty much, so that's going to be a constant. So if our weight decreases, the forces are no longer balanced, and there will be a net upward force, so the droplet will accelerate upwards.